Thank you very much. And I'm going to conclude this. So this will be the third lecture I've given on risk in construction. And I have talked about this topic before. And I will continue to talk about it because it is the biggest single sort of life changer that we're facing, which is, of course, global climate change. So I'm going to talk a little bit about the science behind it, where the science sits right now. In other words, what have the scientists decided as a community, and why we should be worried about it. Now, you might think it's a little unusual that in a class on construction I'm talking about global warming and so forth, but I can assure you that it will impact upon the built environment, and somehow in the future you are going to have to negotiate and deal with the consequences of unpredictable or unprecedented events. And I'll try and give some examples of that as we talk through in order to sort of convince you of its relevance. But I will start right now by saying that we're entering into a period of increased environmental hazards where we are superimposing a heavily altered climate upon an already risky Earth. So we're already dealing with a certain amount of hazards associated with dwelling on Earth, and this is just making things a little bit worse. We're also dealing with an increasingly industrialized landscape, and one that is interrupted by contamination and degradation of various sorts, and that essentially this leads to situations of greater instability. Now I'm going to talk in particular about a few phenomena that are really quite relevant to us, and ones that have been in many ways overlooked, such as heat and cold extremes. So we're used to a climate that's fairly stable, and certain things really throw us off. Now I should point out that we've been busy in the last decade or so in order keeping up with something called sustainability. Sustainability is a broad term, but one of the things it means is producing a built environment that has less negative impact on the global climate change, on the environment in general. So as a result of that, our obsession has been, our main interest has been in conserving energy, keeping things tucked up tight and warm. Well, we're entering into a period now of increased heat extremes. So we may have built, in many cases, a built environment which does not allow natural ventilation to occur, and actually makes the situation of heat extremes even worse. I'll also talk about storms, high winds, and some of the other pressing things which might be directly related to our work, which is sea level rising and the kind of activity that's going to bring about. So we're faced with a situation of having to mostly worry about adaptation and mitigation. So we've passed the point where we're thinking an awful lot about sustainability, and we're thinking more about how to actually deal with the changes that we have upon us. As I mentioned, these are layered upon each other. So the problems of urban heat extremes due to heat island effects, the gradual increase in the temperatures, that's imposed upon an already sort of tough fabric of the city itself, which includes pollution, overcrowding, overburdening of resources, migration, which is not talked about often very much in terms of built environment, but the largest growing urban form is the irregular city, the informal city, the slum. That's the biggest growing form worldwide. So whether we like it or not, we are inheriting a built environment that is far from perfect. I'll talk a little bit about food resilience, and then I won't be able to pass without mentioning transport infrastructure, power supply, and so forth. So anyhow, my approach to this session is really quite broad, and what I intend to do is explain some of the larger issues, and most importantly, I guess, relate why it's important to us. Where are we gonna, what role do we as project managers and constructors and planners and some architects in here, what role do actually we have in this resolving some of these problems? And what extra skills, what extra talents are we going to need to make sure we put it all into place? Is that right? Can you see that? Yeah. Okay. I'll talk about the latest report, or one of the latest. There's been a series of reports from the IPCC, Intergovernmental Panel on Climate Change, and I'll talk about them. They've been very distressing reading, actually, going through these documents. So anyhow, all of you will be at least partially familiar with the greenhouse effect. It's an atmospheric solar phenomenon where the sun's rays heat up the Earth, and the Earth, as you would expect, has natural fluctuations and variations due to the mixing caused by the atmosphere and the seasons, of course. But something has happened since industrial times, or since pre-industrial times, in that we seem to have created a thicker blanket over the Earth, which is preventing much of the heat from escaping, so that the Earth is slowly warming up. This is something that you should be quite familiar with. And of course, all of these gases contribute in some way, and some gases are more sort of voluminous than others, although some of the smaller ones have a greater effect. So carbon dioxide makes up the largest, about 60%. And it's pretty hard to avoid producing carbon dioxide. First of all, we breathe, we produce carbon dioxide. Plants, when they transpire, when they decay, they produce carbon dioxide. Processes in the ocean produce carbon dioxide. So it's you can't get around it. And of course, the biggest and the most unfortunate one is carbon-based fuels. And there's just no way you can get around. There's no way I'm going to get people can get to work in the morning. There's no way they can heat their house without using some part of their fuel supply as carbon-based. But of course, there's carbon embodied in all of our everyday objects. When you go to make a sheet of paper, there's energy involved in producing the paper, but there's a certain amount of carbon that's embodied simply by taking an organic material, squishing it flat, and making it, rolling it out into a flat shape for you to use. So there's embodied carbon in pretty much, well, in everything, in every way of our life, either the energy involved or the actual carbon itself wrapped up in the molecules. And other gases are relevant too. Methane, although it makes up only 14%, has a much stronger effect. Methane is produced by, the big thing is by cows belching. Seems to be one of the biggest causes of methane gas. Right, so globally, we're about, if you average the entire globe, we are somewhere around 0.8 degrees on average above these, what they call the pre-industrial levels. Now that doesn't mean every place is exactly 0.8, or it's not 0.8 at every point of the year. Of course it isn't. It's very lumpily distributed over the Earth. And 0.18 degrees doesn't sound like very much. You probably wouldn't even notice if I turned up the thermometer 0.8 degrees, you probably wouldn't pay any attention to it. But this is, of course, a global average and takes into account a lot of variation and extremes. Now, most alarmingly is that a small change in the mean actually has a big impact on the extremes. So you might increase the mean temperature by 0.8 degrees or 1 degrees, but the extremes might actually the hottest temperature that year, the hottest temperature that month, might be 5 degrees more than normal. So it's the extremes is what we're worried about. We don't really pay that much attention to the averages, but it's the extremes that we're more startled about, the ones that impact us the most. And I guess what hasn't been fully realized in the assessment of climate change is the combined effects. The fact that you have longer periods when it's ever so slightly hotter, but not only are they hotter, but they're a bit drier, and there are periods when there's not much rain. So there isn't much rain in storage either. So you have these wildfires now, which seem to be affecting almost every continent. Every continent on Earth, save Greenland, and Antarctica. Other than that, everything seems to be burning down. And there are wildfires now in Australia, which are shocking. The ones in Siberia haven't slowed down at all. The ones in the western states in America are burning like crazy. A few summers ago, it was the Mediterranean that seemed to be burning. And it's easy to say that these things aren't ascribed to this phenomenon that happened every once in a while. Someone throws a match, but it isn't. It's actually changes in the global climatic system, which render it much easier for things to burn. And of course, the burning does, unfortunately, adds in sort of a negative feedback or positive feedback. They actually produce so much carbon dioxide it accelerates the warming. So there's some fear that some kind of tipping point has been exceeded already. In other words, gone past the point of no return where the Earth is irreparably damaged. So anyhow, this is if anyone asks you about these global warming, we're looking now just at the beginning of this blue line here. So we're sitting just about, is that right? Yeah, we're sitting just about here. And really what we want to know is what's going to happen. So we're sitting right in the middle of this blue line. So this is all observed data right here. And from these wildly wiggly lines, these are global means. From these wildly, we want to know whether it's going this way or whether it's going that way or whether it's kind of leveling off. It's quite hard to say that just because of the inherent sort of variability in this particular data set. So this is an average data set, so it's already been averaged out. It's already been modified somewhat, filtered. But we're trying to make projections about what's going to happen in the next sort of 10 to 15 years in periods. Now there was a period during the 50s and I guess 60s and early 70s when things weren't really warming up that much. It had warmed up significantly during this period around the war, I guess, just in the lead up to the war. And then it kind of flattened out a bit. And during this period, there was still plenty of work going on in global climate research. But everyone was saying, well, things aren't really happening. But this has all changed in the last few summers, where we've had some of the hottest summers on record. And I guess what's provoked everyone to get a little bit more fussed about all of this is that a recent report was published in October of 2018, which was reporting on the 1.5 degree world. There are parts of the world which already have warmed. I told you it wasn't uniform, the warming, but there are parts already that have warmed by more than 1.5%. And as a result of that, a good way to study how the world might look like in a 1.5 degree warming is to look at places where it's already happened. You know, how has this affected parts of sub-Saharan Africa? How has this affected parts of the Arab regions of India, Indian subcontinent? How is it affecting parts of Siberia, which have warmed much greater than any other regions on Earth? So in other words, there's enough of there's enough of a living laboratory for us to investigate these a much greater range or a much greater impact of global warming that we've actually experienced on an average. So the real question we want to know is, what's the big difference between a 1.5 world and a 2-degree world? Doesn't sound like very much, but actually the impact in terms of how it affects our water supply, rain supply, the carbon cycle, all of these things, the thermohaline cycle in the oceans, these things are really on it's really quite startling, the difference between these two. And the way that we know that is because we have a reasonably large testing area to work it through. Now, most people will say, well, this is, natural occurrences, natural fluctuations. How do we actually know that that it's man-made? It's quite an easy argument to say that if we remove the natural variability, the natural variability is so great that actually the human-induced warming is just lost within that. There's a very strong argument. Many people in positions of power are making this argument that it's actually not global warming, it's something else. And the way that we know it is we create a series of computer models. And computer models are very similar in ways, or numerical models, are very similar in the ways that the models used to predict short-term or medium-term weather forecasts. So you go home in the evening and you watch the news and they tell you what it's going to be like the next 5 or 6 days in your neighborhood, in your area. And you believe them. But if you take a sort of souped up version of that computer model and you project it out to 10, 15, or 20 years, you end up using the same physics, it's the same mathematics that governs these models, but it's just set on a different time scale and a different spatial scale as well. So it's global rather than regional, and the time scale is 5 years rather than 5 days. Now, that doesn't diminish it. The physics is the same. The basic principles behind it are the same. It's just that we're using these models differently. They're actually different sets of models, but they have similar things in character. And with these models, it's almost like you're having a whole world on your desktop. You can actually run experiments. And these models are run continuously. So they're global climate models that are running as we speak. And they run them through different scenarios. They remove certain gases and see what happens. And the conclusion is that if they remove all of the man-made gases, there would still be natural fluctuation of the climate, but it wouldn't be anything as upward and anything as convincingly positive or changing as it has been. So there's actually a reasonably robust computer-based argument stating that these are actually man-made causes. Well, is it actually inevitable? And we're going to discuss in a little while what the impacts might be, because I think that would bring it, that brings it a little bit closer to home. But are these things actually inevitable? And the answer to that is no. Well, people don't think so. We're not completely fatalistic yet. And indeed, the United Nations framework, the United Nations, which is this global body which attempts to govern the peace between the nations, actually has set up a unit to deal just with global climate change issues. And they issued a framework, and there was a Kyoto Protocol. There's alternative things. There's a Muslim 7-year action plan on climate change. There's a recognition by the greater powers that actually these things can be prevented. And much of what's gone into education and schooling and institutional change has been around this idea of reducing carbon, sustainability, as I started talking with. The latest iteration of this, of course, of the Paris Agreement, in which it sets standards. It actually sets a cap on carbon emissions, and every country has to pull their weight in actually reducing carbon. And quite depressingly, the United States has more or less pulled out of this and I think other countries have as well. So let's just talk a little bit about predictions. So when you're making predictions, I mentioned that you're using computer models. It's the only way to do it. And we have here a set of observed data, that's in gray. And then superimposed on that, you have the what's considered to be human-induced. So this is using computer models to determine which component of the observed data is actually caused by greenhouse emissions. And you have something called the total forced temperature changes. So this is another one of these man-induced averages. The only problem is these things are they're based on modeling, so there's some error associated with it, and that's what this brown area is right here. So there's some uncertainty about some uncertainty inherent in the way that they've done the modeling. So if the models were absolutely perfect, these might be a little bit narrower, but still, there's no way to escape the fact that these are largely chaotic systems. So getting things, predicting climate is like predicting the shape of smoke. It's the same level of complexity. And so anyhow, the predictions themselves lie within what they believe to be a range. So the worst case scenario would be, I guess by the year 2050, would be just over a degree average globally in temperature. But the worst case scenario is significantly worse than that. It's 1.5 degree. Doesn't sound like much, but it's the global aspect of it that's worrying. 1.5 doesn't sound like much. 2 doesn't sound like much, but it already has happened in certain places. And what does it actually mean? What does it mean for us? You know, where does it sit with us in our careers? I mentioned cold extremes and heat extremes, and even though the mean temperatures might so this is the heat extremes based on land. So even though the mean temperatures might seem to be changing very little, what's interesting or what's relevant is the fatness, the thickness of these extremes. So if we were all very contented with a very narrow and very sharp distribution of temperature extremes, then I think it would be less alarming. But we're looking now at multiple days of extremely high temperatures, and the human body simply doesn't function. Machinery doesn't function. Transport systems don't function over certain thresholds, especially if they're sustained for a number of days. So what really worries us about these the changing temperatures is the impact on the extremes. Now there's other things as well. We're very concerned about 5-day rain periods and what impact these shifts have on the changings in the difference in the extremes. Now there already is reasonable evidence from certain places that extreme rainfalls are getting worse. So if you actually study one little area and you look at carefully how these intense periods, these 5-day heavy rainfall periods, you'll actually they can actually detect a statistically significant change. So anyhow, one thing we do know that it's this complex interplay between natural systems and the man-made environment. And that's really where our role or our interest comes in. I'll skip over this a little bit, these arid regions. So in the end, what we're ending up doing now is acknowledging and accepting the fact that climate change has happened. We've accepted the fact that extremes will be more extreme. And what the challenge is actually building in something called resilience. In other words, making some preparations in order to anticipate unfortunate and sort of but unavoidable changes. I'll just mention that a pretty good place to study where these things are happening, or a pretty good way to study these complex interactions, are in places where it's already happened. And if you just look at these locations here, these are places where we've had experiencing 1.5 degrees to something like 20 or to 40% of the total population. So I think what the red dots are the big population centers, and what the different colors indicates the average temperature going up to around 1.5. So where the areas are in red are areas where I've already experienced a 1.5 degree world. So part of the reason why there's been so much sort of inactivity in this area is that the rich parts of the world, notably North America, California, Europe, well, we haven't really been exposed to it that much. We're not living in this part of Africa, Yemen, parts of the Middle East, north of the subcontinent into the Kush, the Himalayas, and of course the polar regions where nobody lives, but where the change has been even the most dramatic. Anyhow, in the UK we've seen increases of about 0.9% in the years 2005-2014 compared with the early 60s. And we've seen some things like annual rainfall over Scotland increased. Sea level has risen about 1.4 millimeter a year. Doesn't sound very much, but these are still quite early days in terms of the sea level rise. And also, this is global, it covers the whole island. So the warming between the ages of, between the years 2080, near the end of this century, is likely to be around 1.4, between 1.4 and 3.2, depending on how accurate or how reliable our computer models have been. I'm going to skip over a little bit like this. So what's the danger of a 2 degree hotter world? I've told you already that we've experienced something around, I don't know, slightly less than a degree in the UK. We haven't noticed that much. I mean, made the news, and we've had some heat waves, people have died, we've had some water problems, water shortages. We've had some issues with flooding, perhaps greater than we haven't had before. But what would a 2 degree look like? Well, the difference between a 1.5 degree and a 2 degree might be more significant than the difference between a 1 and a 1.5 degree. And that's simply because these combined impacts might add up on each other. So it would exacerbate extreme weather, rising sea levels, diminishing Arctic sea ice. Diminishing Arctic sea ice has two significant impacts. One of them is that it injects all of this fresh water into the oceans, which has an impact on the ocean currents, the circulation systems. And the circulation system, the North Atlantic drift, I guess, or the thermohaline circulation, it's what pulls away heat from the equators and draws it up to the temperate regions. So we owe our lush life in England due to the fact that we have heat transported from the tropics, courtesy of the Atlantic Ocean, the Atlantic currents. But all this fresh water actually could influence the way this thermohaline circulation works. It could alter it, change direction, it could push it further south, or it could shut it off completely. The other impact of the melting ice caps is global sea level rise. And of course, if they're floating, there's no difference. It wouldn't make any difference in the sea level. But of course, the big ice caps on Greenland, on the South Pole, these are the ones where if they started, well, they are melting, but if their melting were to significantly accelerate, then we would start to notice it. And I think on a lot of very fragile estuarian areas, I know that Vietnam, South China, these places are really vulnerable. There are lots of people living on or near the Mekong Delta and these sort of swampy regions. In Bengal, in the mouth of the rivers there, they've always been prone to flooding, and I think that the frequency of those events is just going to be even greater. I'll talk a little bit about coral reefs, but I think I'll skip over a lot. What about the impact of ecology, and why is ecology important for the built environment? We do ecological studies for all of our big projects, and we're committed as developers and constructors not to damage the environment, the natural environment, more than absolutely necessary. And we try to have a minimal impact approach to the use of our land. But 1.5 degree or 1 degree would really impact the sort of biodiversity of this island. And we've already seen the loss of a lot of species. Invertebrates have been terribly hit. Bird life has been decreased over the last 100 years, maybe by 30%. Heating has only been part of that. Certainly pollution is probably more. There are other shifts as well. So the ecology is certainly impacted by this. So is actually mitigation possible? It's actually possible to slow it down, possibly, but it's beginning to look rather negative, rather pessimistic about whether we're really able to impact a significant change. Now, of course, part of what the UN and the IPCC have been doing is trying to figure out, well, what if we stop carbon emissions tomorrow? What if we actually really slow things down? Could we actually deaccelerate? Could we actually bring things back to the way they were? Probably not. And I think what these sort of studies show, and this is a picture of zero, so these are sort of temperatures above on this scale, and these are the emissions showing here. They're quite severe. There's no chance in the world that we're going to cut CO2 emissions to zero. It just will never happen. I'll talk a little bit about sort of geoengineering. There is some hope, or I think there was some hope that you could extract carbon dioxide from the atmosphere, and actually you can extract it. The only problem is, in order to extract it, you need to expend quite a bit of energy. And as most of our energy supply still comes from carbon-based fuels, we're not really solving the problem in that way. And there are other ways to remove carbon, which is through rainforests, but we're busy chopping down rainforests. In fact, the last 10 years in the Amazon forest has been probably the worst 10 years ever. And in the time when we most need it is when we seem to be losing it the quickest. I'll sort of wrap it up a little bit by talking about infrastructure and hazards. Functionally, our infrastructure doesn't really work well when there are lots of extreme events and of all sorts. So temperature extremes, windstorms, heavy rain events, just simply doesn't work. We haven't designed an infrastructure to deal. We have an infrastructure certainly that deals reasonably well with the status quo, but it's this lack, it's this change that's thrown things off a bit. And that there's a series, sort of a combinatorial effect of hazards in infrastructure, such as flooding and erosion, heavier rainfall than normal, stronger winds, higher temperature extremes. So all of these things sort of are combined now. So you have a day of horrible winds, followed by extreme heat, followed by flooding and erosion. So it's the periodicity, the repetition of these events that is going to wear us down. So if we were dealing with just one of them, maybe on an increased rate, we could. But it looks as though, quite convincingly, that it's going to be all at the same time. And of course, we're worried about the impact on goods and services, and sort of added stresses to an already stressed environment. So it seems like the combinatorial effect, the additive effect, and the fact that we've been sort of neglecting our environmental responsibility for such a long time does seem to be catching up to us. I'm quite keen on heat waves. I'm very alarmed about heat waves because they're insipid, and they're not something that it's not a dramatic storm, it's something like that. It's just a picture of a heat wave looks like a picture of something without a heat wave. It's not very photogenic. But the actual increased deaths is starting to register. So it's not uncommon for there to be a peak of deaths associated with heat. Normally we have in the north hemisphere at least there's a cyclical cycle of mortality. It comes around Christmas time. But actually we're seeing heat waves in certain areas, Southeast Asia now. Certainly the heat deaths have exceeded the cold deaths. In North America it's not so relevant. Europe, of course. Central Europe has suffered quite a bit, and there's been some heat waves that have sort of changed public policy as a result of them. There have been thousands of people killed. I mentioned the 2003 heat wave when happened at the worst time in the worst time of the year. That's because people were on holidays. There's a social factor involved. They left the old people back in the cities, and they kind of shut them up in the flats. And they said, "Don't go out," and many of them just suffered. They couldn't cool down in the evening. So even though the nighttime temperatures was relatively cool, they couldn't quite manage to cool themselves down because it had been unusually warm, and usually they were quite accustomed to a certain lifestyle. In France it was quite terrible, partly because of social behavior, the way that they managed their older people. In Italy, the same heat wave happened with hardly any excess death, no noted excess deaths. That's just because the Italians tend to bring their parents and grandparents with them when they go on holiday. But anyhow, it's a significant public health attributed to something, I don't know, 30 or 40,000 deaths in the UK alone. Now, a lot of it, I mentioned these sort of combinatorial effects. A lot of it has to do with the sort of modern nature of cities. When you have transport barriers, you have exclusion zones, sort of leafy suburbs separated. You have informal settlements. You have waterways that are blocked off through circulation. You have interruptions to the subsoil, subsurface water, and so forth. So there's the overlaid upon the normal disruption of urban life is the imposition of heat extremes. And of course they need some sort of management. That's what we're about, I guess. And so I think I'm just going to. I think I've laid on enough for you today, and I will finish this lecture. I'll talk about this in more detail next week. But I think I've given you enough to get you started on this topic. Anyhow, thanks very much.